Okay, welcome to your Chapter 8 introductory video. As is the case often in general chemistry, this chapter follows directly from the previous chapter, and both of these chapters will be imperative for, Gen Chem 2. What we're basically going to be doing here is applying things like stoichiometry and more or less moles to solutions. So we'll be looking at aqueous solutions. This is very important for biology, of course, for environmental chemistry. The stoichiometry stuff will come more in Gen Chem 2, where you do a lot of aqueous stoichiometry. Specific learning goals, the main thing here is going to be able to carry out calculations involving molarity. And if you've mastered moles, then you'll have no problem with this. If you're still struggling with moles, then that might be an issue. But basically, you'll be able to calculate things like the amount of solute, the volume, not just molarity. Ultimately, at the end, you'll be able to predict products of reactions, mainly simple ones, things like precipitates. You'll need to be able to identify acids and bases. And a topic that's a little tricky will be important in Gen Chem 2. We introduced it here in Gen Chem 1. That is oxidation states for electron transfer reactions, which are some of the more common reactions you'll see. These are key terms to know. They're throughout the chapter. I'm not going to go through all of these. Some of these you're introduced to in lab also, but I'll touch on some of them certainly. We'll have an equation dealing with dilutions. I'll definitely define acids and bases. We'll talk about precipitates and electrolytes. These are pretty basic. You probably know already. Here is the chapter outline. Of course, I'll be starting right here, solutions and their concentrations. We won't be doing ion exchange, there just isn't time for it. If I have a little time in class, I will talk about what ion exchange is because it's an interesting application. So solution concentration, you might have done this in lab already. We can define the amount of solute in a solution, and you can do that several ways. You could do it in mass over some sort of volume, or you can do moles over some sort of volume. So there's different approaches. And of course, in chemistry, we tend to use moles, and that's going to be what we're going to do. We're going to look at molarity. So this is molarity here, and I don't want you to get confused by this slide. This part down here is a little confusing. Let's hold off on that. Molarity with capital M is simply moles of solute per liters of solution. Notice it's liters of solution, which is the total volume when you're done. Because the solute does take up space in the solution, as you might imagine. If I put a bunch of sugar into a glass of water, that volume will actually increase once you add the sugar to a fixed volume of water. You won't be able to see it visibly, but you could measure it, and there will be a difference. So it's the total volume of the solution that becomes important in how you make up the solution, which I'll show you a slide of in a second. But of course, moles can always be gotten from the molar mass of a substance. If you know the mass, you can simply multiply by the molar mass to get the number of moles, correct? I mean, the molar mass, of course, just coming from the periodic table, you're just going to take the elements, add them up. If it's sodium chloride, you'll add up sodium and chlorine, and you'll put that in units of grams per mole. That's what molar mass is. So obviously, if you have the mass of a substance, grams, X amount of grams, you can multiply that by the reciprocal of the molar mass. Let's just say there's 23 grams per mole, okay? And then looking at dimensional analysis, of course, your grams cancel out, and you now have the moles. And of course, if you were given a volume, particular volume it was in 100 milliliters. Well, 100 milliliters is that many liters, and this is always in liters. That's one of the keys. This down here looks a little confusing, but all it is showing you how we can use molarity as a conversion factor. So effectively, if you want to know the mass, here I was given the mass over here. If you want to know the mass and you know the volume, well, simply by multiplying the molarity, because this right here is the molarity, capital M, by the volume, gives you the moles. And then you can multiply by your molar mass. This is your molar mass to get your grams, looking at your units, you see? That's all it is. It's just dimensional analysis. So just keep that in mind. Always use your units as a way of figuring out what it is you need to multiply by to get what you want. These are just some ways we can represent units in smaller units, millimolars and micromolars. Those are two common ones. Dilutions, you might have done this in lab already, so this is the one where we look at, some people write it as M1V1 equals M2V2. Some people use concentrated instead of 1 and 2 and dilute. Some people use initial with I's and some people use F for final. It doesn't really matter. Just realizing that the volume times the molarity, the units for molarity is moles per liter. So if I'm multiplying it by liters, I'm getting moles. So in a dilution problem, if I have a given solution and all I do is add some water to it, the number of moles is the same. And that's the whole nature of this equation. It's saying the number of moles equals the number of moles, and that's true. And you answered that question to some of you on a pre-lab that you had to do. And realizing that the amount of substance that in there is the same, and that's the nature of this equation. So if you have 3 of these, you can always calculate the other one. It doesn't matter. You might be asked the initial molarity you need. You might be asked the initial volume needed to make up the solution. You might be asked the final molarity, whatever it is. This equation is very simply manipulated to answer any of those questions. Now, when you're actually making a solution, and this is just an important point, is that when you're dissolving, I teach my students this time all in my research lab, you would add your solute there and get it dissolved, okay, and then in the end, you don't want to add, like, so for instance, you want to make up a 1 molar solution of sodium chloride. You don't measure out a liter and then add the mass of sodium chloride you need to make a 1 molar solution, because that will result in a volume greater than 1 liter and a molarity that is less than 1. It'll be slightly off, and for analytical chemistry or exact, you don't want to do that. So what you do is you get it dissolved in a smaller volume here, something less than the liter, then ultimately you bring it up to volume using something like this, a squirt bottle, up to the line. Once everything is dissolved, that's the proper way to make a solution. Electrolytes. What I have here is 3 figures. What I have on the left are non-elect. Oh, wait a second. I thought I had B, C, D, and E. Okay, so, okay, yes. So let's start on the right here. This is an electrolyte, a strong electrolyte. Strong electrolyte basically produces a bunch of ions in solution. Basically, all the sodium and the chloride in the sodium chloride become ions, and you can actually get really good current and light a light bulb. It will carry the electricity, which you got just 2 electrodes here. They're unconnected, and actually current can be carried by the ions in solution. A weak electrolyte is one that only produces a small amount of ions in solution. Acetic acid is an example of one of these, and we'll talk about acids a little bit later. What basically means that when I put this into solution, it only does this to a small extent, produces these ions. Most of it's still in this form. So you can see you don't get a real lot of current. And then on the left over here, I have non-electrolytes that don't do anything in solution. So your molecular compounds, your covalent compounds, remember, that don't have any metals, they will not form ions in solution. Here's my metal here. This forms ion in solution. Now, this is an acid. That's the key. That's what we're going to talk about. Acids can form ions in solutions and not have a metal. That's one of the things you need to learn. But if it's not an acid and it doesn't have a metal in it, then it's not going to form ions in solutions unless it's a base. And we'll talk about bases also, but you're not going to have to deal with any organic bases. And this is really the only organic acid you have to deal with. Also, if I had solid sodium chloride, and that's what this is here. It's tough to see from the picture, but that is just the salt. You see, that's not going to conduct electricity because the ions aren't free from the crystal lattice. You need to put them in water to do that. Okay, acids and bases. Simple definitions here. Acids produce hydronium ions in solution. You see it down here. Here's hydrochloric acid. You work in the lab. It reacts with water to produce this and this. So the hydrogen goes over here, and the chloride is free. Now, a lot of people will just write this like this, and this is just shorthand notation, and that's fine. But molecularly, this is what's correct, and that's what happens in solution. So these two are, if you will, synonymous. Bases are the opposite. They produce hydroxides in solution. So if you add an acid and base together, you get water because a base produces this, acid produces this. Together, they give you water. Effectively, they neutralize each other. Another way to look at the definition, acids are proton donors, okay? There's the hydrogen ion, which is just a proton because the main isotope of hydrogen has no neutrons. If you remember this notation, right? It's got one proton, no neutrons. Therefore, we call it a proton. That's all it is. And you should realize that subatomic particles are not stable when they're not associated with matter. So this has to go somewhere. And this is the best place for it to go. And what I tell you about in general chemistry, everything works towards a lower state of stability. So effectively, it's more stable with the water than it is here with the HCl. Another way to define bases is proton acceptors. So they're always going to be opposites of each other. Now, when we talk about strong and weak, that has to do with its molecular structures, nothing to do with the concentration. I can make a weak acid very strong and a strong acid very weak. A strong acid or base just completely dissociates in the water. And it means there's nothing left of the original molecular form. So HCl goes completely to H positive and Cl negative. So these are the strong acids. If you memorize those and you see another acid, then you can assume it's weak. And that's going to be important in Chem Chem 2 also. Strong bases, same thing. They completely dissociate or ionize in solution. So there's little left of this. And there will be some, but it's insignificant is the idea. Water's kind of interesting. It can act as an acid or a base. I'm not going to spend a lot of time on this. I'll talk about it a little bit more in class. But basically, it just depends on the environment. And a lot of these things, when we talk about weak acids and bases, really depends on how they behave in water. Well, if it's not just pure water, it depends on the environment, what else is in there. So here, water's acting as as a base. It's accepting the proton from the hydrogen, from the hydrochloric acid, and that's what a base is, right? A proton acceptor. So it acts as a base there. Over here, it acts as an acid because this is a base. And this is one of these bases that doesn't have the hydroxide in it. So you need to memorize that ammonia is a base. And you see why it's a base. It accepts the proton here from the water. So there, water's acting as an acid. So it really depends on its environment. So as I mentioned before, reaction takes place when acid or base react. You're going to get a salt and water. And as an example, just take sodium hydroxide plus HCl. What do you get? Well, swap partners, right? Double displacement reaction, metathesis reaction, you get H2O plus NaCl. NaCl is not the only salt. That is table salt. But anytime the anion comes from the acid and the cation from the base, we call that a salt. So I could have wrote this with potassium hydroxide and hydrobromic acid. And I'd have water and KBr would be my salt. Now, this gives students a lot of problems, and when you do this in lab, you see that it creates a lot of problems. The molecular equation is the complete balanced equation, and this one is balanced already, showing all of your species in their molecular form. The overall ion equation is writing anything as ions that exist as ions in solution, and that is three things: strong acids, strong bases, and soluble salts. And that's why you have to learn your solubility guidelines. You might have seen that in lab, but you're also going to see it here. So, strong acid, we're going to write it as ions. Strong base, write it as ions. Soluble salt, write it as ions. Water, leave as water. Hence, cancel out anything that occurs on both sides as we did before. Chloride, chloride. Sodium, sodium. What am I left with? I am left with H positive plus OH minus gives me H2O, your net ionic equation. So you need to learn the solubility rules because you have to be able to recognize when a precipitate forms. The one in lab is actually pretty well laid out, and some of them are going to vary. Different textbooks draw their lines different places because you have to realize, and I tell my students this all the time, pretty much everything is soluble in everything. It just might be soluble to an incredibly small extent that it's not even measurable. So we say it's insoluble. But most books use a guideline, a cutoff that says, okay, anything less than this we call insoluble. And that might vary from textbook to textbook and from person to person. And if you talk to different people, one person will say, oh, that's very soluble in water, and the other person will say, oh, it's not very soluble at all. Because it really depends on their perspective of what they consider soluble or not. So these are the rules, and I'm not going to go through this chart. You have it in your book. You have a lab. But when you look at a reaction like this I think, is actually very similar to what you might be doing in lab or have done in lab. And if I take lead nitrate, nitrates are always soluble, no exceptions. And I don't particularly care for this table. It's not very well laid out. But there's nitrates right there. Always soluble, no exceptions. So lead nitrate's going to be written as ions if you were to write your net ionic equation. And group 1 metals are always soluble, no exceptions. So if I was to write this, I would write lead 2 plus NO3 minus, because this is balanced already, we're okay. Well, actually, we have to see that. Let's write the products. I'm going to swap partners. Oh, wait a second. I messed this up here. Plus lead. Oh, this is a mistake here, actually. That has to be 2, because lead is 2 plus 2 nitrate gives me, and I'll write the product down here as I'm getting confused. Running out of room here. Oh, wait a second. I wrote the lead nitrate. This should be sodium here. Let's get rid of this and make that sodium ions. And I wrote nitrate twice also. Unbelievable. And it's back here. Sodium iodine, that's fine. But that should be lead. This should be 2 nit here. Okay, there should be 2 lead nitrate. That's a mistake. So the products, I'm just going to swap partners. So I'm going to say lead iodide, and I'm going to need a 2 there. Plus, and how do I know that? Sodium nitrate. How do I know that? Because lead is 2 plus and iodine's minus 1, so I'm going to need 2 there. So ultimately, your balanced equation, you would need to have the 2 out in front of here, and then ultimately you need to have a 2 here to balance it. But you swap partners, and then you realize you go to this guideline here, and you say, okay, nitrates are all soluble. Oh, lead iodide, the iodides are actually insoluble. That's my precipitate. That's the yellow you're seeing here. That's going to be written as a solid. This ultimately will be written as ions in aqueous. I wrote this final here as molecular, so this would be 2 sodium ions plus 2 nitrate ions, and you can see those will cancel out. And your net ionic equation ultimately will be the lead 2 plus 2I negative gives you PbI2 solid. That will be your net ionic equation. So you've got to know your solubility guidelines. Oxidation reduction. This is the last thing I'm going to cover here. I think I have something else after this, but I don't want this video to get too long, and that's just a couple terms. Oxidation, reaction that increases the oxygen content of a substance. That's one way to define it. Reduction, loss of oxygen. But a better way to look at them is always with electrons, because that definition applies to everything. Some reactions will not have oxygen, and they will be oxidation reduction reactions. You're going to want to look at the transfer of electrons, really. But for right now, all I need you to do for class is to start to get familiar with these oxidation numbers. And we'll do this in class, and these are rules. So look these over and start to understand how we assign oxidation numbers. And then you can actually look at a reaction and tell what's happening in terms of electrons being transferred. And then the last section is just titrations. And you're not going to have to do any major titration calculations. Your book has a lot more that we're going to do. We'll save some of that for Gen Chem 2, but even there I don't emphasize it. I'll show you the basic kind of titration calculation you need to do, and it's kind of like a neutralization. But just get familiar with some of these terms so you know what we're talking about in class. And this is how you do a titration. There's your burette, and you've got maybe some unknown acid amount here, and you want to know what the molarity of this is, and you're going to deliver sodium hydroxide, and you're going to know the concentration of this because you made it up. And by knowing the concentration of this and the volume you deliver and the volume of your unknown sample, you can actually calculate the molarity of your unknown. And we put in indicators to show that change color that show when actually the acid and base have been added in equal amounts and have been neutralized. And by knowing that, you can actually calculate that molarity of the unknown. With that, that concludes the video. So be sure to watch this before lecture.